Mars may be holding its first true chemical signature of ancient life, and Perseverance has just dug it out. At the Neretva Vallis Delta, the rover uncovered a microscopic architecture that should not exist on a sterile planet, tightly layered concentric microspherules built with the same iron-driven pattern, found on Earth where microbes draw energy from minerals. Here the chemistry forms a clear polarity. Reduced iron at the core, oxidized iron at the rim, creating a pattern that biology produces with remarkable consistency. If this is not life, it is an imitation so precise that it challenges our understanding of planetary chemistry itself. To uncover the truth, we must follow Perseverance to the Cheyava Falls outcrop, the ancient archive where this mystery began. The Neretva Vallis Delta stands as a silent monument to a vanished world. Here, billions of years ago, a massive river system raged, carving deep channels through the Martian crust and depositing layers of mud that time would eventually harden into stone. Today, the only movement in this frozen amphitheater is the slow, deliberate work of the Perseverance rover. Operating as a solitary field investigator on a desolate frontier, the rover has focused its attention on an arrowhead-shaped outcrop known as Cheyava Falls. To the untrained eye, it appears to be merely another dusty boulder in a sea of red. But through the rover's high-resolution sensors, the rock reveals a chaotic and complex history. Stark white veins of calcium sulfate crisscross the reddish surface like scar tissue marking ancient fractures where mineral-rich water once forced its way through the stone. These veins are the initial evidence proof that this specific location was once a chemically active junction of water and rock. Yet the most startling discovery is not the white veins, but what lies sandwiched between them. On the surface, Cheyava Falls looks like any sedimentary cliff. But under the rover's instruments, a hidden microarchitecture emerges, a pattern so deliberate it forces us to look closer. Scattered across the reddish canvas of the Cheyava Falls rock are hundreds of millimeter-sized formations that defy the chaos of random geology. These are the concentric microspherules, colloquially nicknamed leopard spots by the mission team. And they represent a startling deviation from the surrounding stone. To the naked eye, they appear as irregular splotches, but under the scrutiny of Perseverance's Watson camera, a deliberate geometry reveals itself. Each spot is characterized by a stark off-white core surrounded by a sharply defined dark red rim of hematite, creating a target-like appearance that stands out vividly against the oxidized background. Embedded within and around these halos are even smaller grain-sized structures known as oxidation gradient mineral spherules, or poppy seeds. These are not mere discolorations. They are complex mineralogical distinct zones, where the chemical state of the rock has been fundamentally altered. In the geological record of Earth, specifically in the ancient red sandstone beds of the Pilbara Craton or the Colorado Plateau, such patterns are rarely accidental. They are the classic fingerprints of chemical disequilibrium, places where the natural thermodynamic state of the rock was forcibly reversed. The precision of these rims implies a localized reaction that spread outward from a central point, suggesting that whatever created them was discrete and active. In purely abiotic geology, minerals tend to settle in layers or veins. They do not typically organize themselves into hundreds of isolated concentric bullseyes without a catalyst to drive the process. Here in the desiccated silence of Mars, we are seeing a pattern that on our home planet is inextricably linked to the presence of biology. Shape alone is never enough. The real story lies not in what these spheres look like, but in how they formed. To understand the leopard spots, we must stop thinking of them as stains and start viewing them as spent fuel cells. In the universe of the cosmic alchemist, life is essentially an electron transport machine, a system that steals energy from the environment to maintain order. On modern Earth, complex life powers this machine using oxygen, but in the suffocating, oxygen-poor environments of the early solar system, life had to be resourceful. It turned to the bedrock itself. The mechanism operating here is known as dissimilatory iron reduction, or DIR. In this process, ancient microbes acting like biological batteries would have attached themselves to oxidized iron in the sediment, a mineral we know as hematite. Hematite is essentially rust iron that has already lost its electrons. for a microbe seeking energy that rust becomes a natural cathode. By pushing their excess metabolic electrons into the solid iron, these organisms reduce it, shifting its chemical state from the red insoluble form of iron 3 to the pale soluble form of iron 2. This atomic transmutation dissolves the red pigment, creating the bleached white core we see in the Cheyava Falls samples. The iron, now mobilized by the microbial current, diffuses outward until it hits the surrounding rock, where it reoxidizes and precipitates, forming the dark, iron-rich rim. What remains is a permanent record of a microscopic energy harvest. These spots are the visible scars of electrons being ripped from the crust to power the first flickering sparks of a biosphere. It is a metabolic signature etched in stone, a testament to a time when the very rocks of Mars served as the life support system for a hidden ecosystem. But even an elegant mechanism needs raw ingredients. And here Mars reveals something unexpected, a trio of elements that on Earth define the foundation of biology. As Perseverance brought its PIXL X-ray analyzer and the SHERLOC spectrometer onto the target, the readings revealed a chemical pattern that is statistically unlikely to arise from ordinary geology. The spots are not simply variations in iron. They sit at the intersection of three elements essential to biology: iron, carbon, and phosphorus. Iron provides the energy gradient. Carbon provides the structural framework for organic molecules. But the presence of phosphorus is the smoking gun of cellular complexity. On Earth, phosphorus is the currency of life, forming the backbone of DNA, RNA, and the energy-carrying molecule ATP. It is often a limiting nutrient hoarded by living things. In abiotic environments, phosphorus is usually dispersed diffusely throughout the rock. However, in the Cheyava Falls samples, the phosphorus is concentrated specifically within the leopard spots. This localization suggests a biological hoarding mechanism, microbes gathering scarce nutrients from the environment and concentrating them within their cellular communities. When these communities died and decayed, they left behind enriched pockets of phosphorus locked inside the iron-reduced halos. The simultaneous detection of organic carbon compounds trapped within these same zones completes the triad. We are not looking at a single element behaving strangely. We are looking at the three pillars of biochemistry converging in the exact same millimeter-scale locations. This chemical architecture, energy source, building block, and fuel currency, co-located in a structure identical to microbial fossils on Earth, is the strongest chemical argument for life ever found on the red planet. Yet chemistry does not exist in a vacuum. To judge whether these microspherules could be biological, we must step back, far back. Because structures are only as meaningful as the environment that created them. The existence of a biological battery requires more than just machinery. It requires a factory floor. To find it, we must mentally flood the Jezero Crater, turning the clock back 3.5 billion years to the Noachian-Hesperian transition. In this era, Jezero was not a dust bowl, but a dynamic aquatic system. A lake spanning 45 kilometers in width, fed by the rushing waters of the Neretva Vallis River. The evidence for this aquatic past is written in the geometry of the land. From orbit, the distinct fan-shaped delta at the crater's edge is unmistakable. In geology, such specific architecture cannot be forged by a catastrophic, momentary flash flood. It requires the sustained rhythmic pulse of a river flowing for hundreds of thousands, perhaps millions of years. This river acted as a planetary conveyor belt, eroding the highlands and transporting tons of fine-grained sediments, rich in iron, carbon, and phosphorus, into the tranquil basin below. As the water slowed upon entering the lake, it deposited its load building, the delta layer by layer. It is here that the sedimentary archive was constructed. The muds of Jezero are rich in two specific mineral classes, smectite clays and carbonates. For an astrobiologist, this combination is the holy grail of preservation. Smectite clays possess a unique molecular structure capable of swelling and trapping organic compounds between their silicate sheets, shielding them from the destructive effects of oxidation and radiation for billions of years. Meanwhile, the carbonates found along the ancient lake margins suggest a robust interaction between the water and a thick, carbon-rich atmosphere. On Earth, such carbonate platforms are the cradles of life, often preserving the oldest known fossils, such as stromatolites. In Jezero, they act as a geochemical vault, locking the leopard spots in a mineral embrace that has survived eons of planetary desiccation. Reconstructing the lake tells us where these rocks formed, but to understand how they stayed warm enough for chemistry to flourish, we must confront a deeper problem, the ancient Martian climate. Reconstructing the lake tells us where these rocks formed, but to understand how they stayed warm enough for chemistry to flourish, we must confront a deeper problem, the ancient Martian climate. The existence of liquid water on ancient Mars presents a formidable physics problem known as the faint young sun paradox. 3.5 billion years ago, our star was in its stellar infancy, shining with only about 70% of its current luminosity. Under such weak radiation, standard climate models suggest that Mars, positioned 140 million miles from the Sun, should have been a frozen wasteland of dry ice incapable of sustaining the flowing rivers that carved Neretva Vallis. The solution to this paradox lies in the atmospheric alchemy of the Noachian era. Carbon dioxide alone, even in a thick atmosphere, would not have been a sufficient insulator to prevent global freezing. However, recent climate simulations suggest that Mars possessed a secret weapon, a greenhouse resonance effect created by the interaction of carbon dioxide and hydrogen. In this dense primordial atmosphere, molecules of CO2 and H2 did not merely coexist, they interacted through a phenomenon called collision-induced absorption. As these molecules collided billions of times per second, they temporarily distorted each other's electric fields, creating a supermolecule effect that absorbed infrared heat far more efficiently than either gas could on its own. This created a powerful planetary blanket, a hazy violet-tinted thermal shield that trapped the meager heat of the young sun. It was this delicate atmospheric architecture that pushed the planetary temperature above the freezing point, allowing the hydrologic cycle to churn and the delta at Jezero to grow. Yet a warm planet is only half the equation for life. Biology requires energy, and before the evolution of complex photosynthesis to harvest the sun, life had to look downward into the crust. Ancient Mars was not just a passive rock, it was a thermodynamic engine driven by a process called serpentinization. This is the cosmic alchemist at work on a planetary scale. When water from the Noachian rains or aquifers seeped deep into the crust, it reacted with ultramafic rocks rich in minerals like olivine and pyroxene. This contact triggered a violent exothermic reaction. The water literally hydrated the rock, transforming the crystal structure into new minerals like serpentine and magnetite. But the most critical byproduct of this reaction was gas-pure, energy-rich molecular hydrogen, H2. For the earliest life forms, this hydrogen was the free lunch of the cosmos. It bubbled up through hydrothermal vents on the lake floor and seeped through the porous bedrock of the delta. This geochemical flow provided the essential electron donor for chemolithotrophy, rock-eating life. It suggests that the microbes potentially responsible for the Cheyava Falls spots didn't need to wait for the sun to break through the clouds. They were plugged directly into the planet's geological metabolism. Mars offered both the greenhouse warmth and the hydrogen fuel required to ignite the earliest steps of a biosphere. Yet even the most promising environments can change, and on Mars the change was irreversible. A planet once capable of running Earth-like chemistry began to fall silent. The golden age of the Noachian era was sustained by a delicate balance of internal heat and atmospheric density. But Mars, being half the size of Earth, was destined to age faster. About 3.7 to 4 billion years ago, the planet's internal dynamo, the churning molten core responsible for generating a global magnetic field, began to falter. As the core cooled and solidified, the magnetic shield that protected the planet flickered and died. This was the beginning of the Great Stripping. Without a magnetosphere to deflect the onslaught of the sun, Mars was left naked before the solar wind, a stream of charged particles traveling at nearly 1 million miles per hour. This stream slammed directly into the upper atmosphere, initiating a catastrophic process known as sputtering. Data from NASA's MAVEN mission, Mars Atmosphere and Volatile Evolution, has allowed us to visualize this planetary erosion with remarkable clarity. High-energy solar particles transferred their momentum to atmospheric atoms, knocking them loose from the planet's gravitational grip and sending them drifting into the void. The planetary blanket that had kept Jezero warm was stripped away layer by layer, As the pressure dropped, liquid water could no longer exist on the surface. It either boiled away into the thinning air or locked itself into subterranean ice. Simultaneously, ultraviolet radiation, no longer filtered by a thick atmosphere, began to bombard the surface, breaking apart water molecules in a process called photodissociation. The lightweight hydrogen atoms escaped into space, lost forever. The heavier oxygen atoms, however, remained trapped. With nowhere else to go, they reacted with the iron-rich crust, literally rusting the planet from the outside in. The blue-gray world of the Noachian era slowly turned into the red desert we see today. For the biological potential of Mars, this was not merely a climate shift. It was an existential siege. But biology is stubborn. On Earth, when environments turn hostile, life does not simply vanish. It retreats and adapts. As the surface became sterilized by radiation and desiccation, any hypothetical Martian biosphere would have been forced to execute a bunker strategy. This transition offers a new poignant perspective on the Cheyava Falls discovery. The concentric microspherules may not represent a biosphere in its prime, but one in defensive contraction. In the lens of the xenoprofiler, these structures could be interpreted as the geological footprint of a survival mechanism. As water became scarce and radiation increased, microbial colonies may have clustered tightly together using the iron reduction process, not just for energy, but to build mineralogical shields. The hard, oxidized hematite rims of the leopard spots might have served as a microscopic fortress, a bunker, formed by the colony's own metabolism to seal in remaining moisture and filter out lethal UV rays. These spots, therefore, are likely not the signs of expansion, but of metabolic optimization during a period of environmental decline. They are the fossilized record of life digging in, moving from the open waters of the lake into the pore spaces of the rock and eventually deeper still. But life, if it ever emerged, rarely disappears overnight. It adapts, and the Martian subsurface may hold the last echoes of that adaptation. What began billions of years ago may not be entirely gone. Today's Mars still sends faint chemical signals, and each one hints at a biosphere in deep suspension. The surface is a radiation-soaked desert, but beneath the crust, where temperatures stabilize and pressure mounts, the conditions for life may still exist. The key to this potential survival lies in a chemical paradox. The Martian soil is rich in perchlorate salts that are toxic to humans, but possess a unique ability to absorb water from the atmosphere. In the frigid darkness of the subsurface, these salts can lower the freezing point of water to -70 degrees Celsius, creating pockets of liquid brine that remain fluid even in the deep planetary winter. For the subsurface explorer, these toxic brines are not dead zones, they are refuges. On Earth, we find organisms known as halophiles thriving in similar environments, from the crushing depths of Antarctic salt lakes to the microscopic fissures of deep mine rocks. If Martian life followed a similar path, it would likely exist in a state of cryptobiosis, a profound biological stasis. These are not active, thriving colonies, but dormant microbial candidates, their metabolic clocks slowed to a near halt, repairing DNA damage, and waiting for fleeting moments of liquidity to wake and replicate. The evidence for this sleeping biosphere is elusive yet persistent. The most compelling clue comes from the Curiosity rover, which has detected seasonal pulses of methane gas emanating from the Jezero Crater. On Earth, methane is a primary byproduct of metabolic activity, the exhalation of life. On Mars, these spikes appear in the summer and fade in the winter, mimicking the rhythm of a breathing planet. While geological processes like serpentinization can also produce methane, the seasonality of the signal leaves the biological door wide open. This is not a ghost story. It is a search for biochemistry in suspension. We are looking for a biosphere that has learned the ultimate patience enduring in the dark for eons. But evidence is not certainty, and planetary science carries a long history of misinterpretation. Before we decide what Mars is telling us, we must revisit the lessons of the past. But evidence is not certainty, and planetary science carries a long history of misinterpretation. Before we decide what Mars is telling us, we must revisit the lessons of the past. The road to discovering alien life is paved with false positives moments, where chemistry successfully masqueraded as biology. In 1976, NASA's Viking landers conducted the famous labeled release experiment, which detected a rapid release of carbon dioxide from Martian soil, a classic signature of metabolism. The world held its breath, believing we had found life. Decades later, however, we learned the truth. The reaction was likely driven by perchlorates, the same highly reactive salts that now tantalize us with liquid brines. It was a chemical mirage. 20 years later, in 1996, the Allen Hills 84,001 meteorite shocked the world again. Inside this Martian rock, scientists found microscopic structures that looked identical to fossilized bacteria. Yet rigorous analysis eventually proved that these nanobacteria were likely formed by high-temperature geological processes, not biological ones. These failures were not setbacks. They were necessary inoculations against wishful thinking. They taught us that morphology shape alone is never enough. To navigate this ambiguity, NASA created the COLD scale, short for Confidence of Life Detection, a 7-step framework designed to evaluate extraordinary claims with rigorous scrutiny. The discovery at Cheyava Falls, despite its compelling chemical triad and leopard spot architecture, currently sits only at the lower rungs of this ladder. It is a zone of potential, not a verdict. To climb higher, we need tools far more powerful than any rover can carry. And so the question remains unfinished. The only way forward is to bring Mars to Earth to let our laboratories answer what our rovers cannot. The Mars Sample Return Mission. Bifront MSR plan for the 2030s represents the final stage of this multi-generational effort. When the samples from Cheyava Falls eventually land in terrestrial containment facilities, they will be subjected to atom-by-atom dissection. We will look for chirality in amino acids, isotopic fractionation in carbon, and the intricate molecular machinery that only life can assemble. The answer hidden in those rocks will trigger a profound philosophical shift, regardless of the outcome. If we find that life did emerge on Mars, even briefly, it confirms the cosmic imperative that life is a natural, inevitable consequence of the universe's laws, and we are merely one of countless biological islands. But if the rocks are truly dead, if Mars had water, energy, and time yet remains sterile, it forces us to confront the rare Earth hypothesis. It would suggest that the leap from chemistry to biology is incredibly difficult, and we may be terrifyingly alone in the void. Perseverance has done its part. It has found the anomaly. It has packaged the evidence. Now the red planet waits for us to complete the journey. The story of life on Mars is no longer just about what is out there. It is about understanding the fragility and miracle of what is right here.